Hello everyone, welcome to my channel Cosmoki. In this lecture, we'll be talking about the question all possible full binary trees. We are given an integer n and we have to return a list of all possible full binary trees with n nodes, where each node will be having a value as 0. We are having that we need to return the final list of trees in any order. And a full binary tree is a binary tree where each node has exactly 0 or 2 children. So, let me explain what the question says. A full binary tree is the one which has either 0 child or 2 children. So, in case of n is equals to 5, what the possibility of having a full binary tree is, we'll be starting first from this possibility, where we are having the root node, then we are having its 2 children, and then further it has a left subtree consisting of 2 children, or we can say the 2 leaf nodes. Then there is another possibility for n is equals to 5, where we are having right subtree here having 2 leaves. In this case, we are having leaf nodes from the left subtree. In this case, we are having the leaf nodes from the right subtree. We can see that there are no more possibilities for generating full binary tree where n is equals to 5. Let's understand some more example where I will be taking n is equals to 4. First, we will be having a root node. Then we will be having its 2 children. Then here a conflict arises because we are having n is equals to 4 and we have already created a tree where we are having the 3 nodes. But we need one more node to be added. Now the question arises, we just need to add only one tree here, and if we'll be adding either here or here, it will create a conflicting situation because in the question we have been asked to generate a full binary tree, which will conflict over the situation that we'll be having either 0 child or 2 children, because here we need to take one child either in the left subtree or in the right subtree. But we can't do that because we have been given that we have to generate the full binary tree. So we need to accept the situation of having either 0 child or 2 children. But we can't do this in n is equals to 4. Now let's consider n is equals to 6. Let's take another root node, then its 2 children, then we are taking everything in the left subtree only, starting from the left subtree. Then we'll be having another 0. So let's count how many number of nodes are there. Till now we have n is equals to 5, but we need 6. Now again the conflict arises here also because in the question we have been asked to generate a full binary tree, but for generating 6 we either need to add one node either here or here. But we can't do that because we have been asked to generate a full binary tree, which again conflict over this situation. So one observation we have from the above examples that we cannot have full binary trees with even number of nodes. Even if you will be taking the base case where n is equals to 2, you can see we'll have to take the root node and one more node we need. So either we'll be having here or we'll be having here. But this is exceeding the number of nodes because we just need to, and but for the minimal case we need to have 3. Either 1, minimal case is the 1, but if we are exceeding 1 then we'll need to have the 3 after 1. We can't have 2. Alright. So one observation, this is the most important observation. This is not visible. So what we have concluded till here, that we'll use this condition as soon as we'll write our code, that we cannot have even numbers when we'll be writing our code. So we'll be using this condition. Okay, let's start with another observation. Now we'll be considering only the odd nodes. So you can even see that here, in case of n is equals to 5, here we have 3 nodes and here 1. Again, in this side also we will have 1 and here we are having 3. Now for n is equals to 4 we don't have to consider, as I've already told the reason. Now if I will be taking for n is equals to 7, you can see the possibilities are here we are having 3, here we are having 3. That means 3 number of nodes in the left subtree and 3 number of nodes in the right subtree. Similarly, there are other possibilities too, where we will be having number of nodes here as 1 and number of nodes here as 5. Similarly, the other possibility is having the number of nodes here as 5 will be like this, and number of nodes here as 1. So we can easily observe one condition over here, that for each node we need to consider, for generating a full binary tree we need to consider this condition, either considering I as a variable and the other has to be n minus I minus 1. Now why did I take this? This will be clear to you in the further explanation. Let me explain you this question through the code. I've used the dry run, how I'll be generating it. So I am using the dry run for n is equals to 5. You can see what I have done is I have taken a vector of data type as tree node star. You can see that this stores all the possibilities of a particular full binary tree for a particular value of n. Here n is equals to 5. We are taking a list, naming it as list. Then we will be traversing from 1 is equals to till the whole possibility. That means we will be traversing from 1 to 5, leaving all the even numbers. We will be just taking odd numbers in this case. That's why we have this condition I plus is equals to 2. Then we can see what we can do. We'll have to generate a left subtree. For generating a left subtree, we need to store it in again in a list of type tree node. So you need to initialize this here itself. I have not shown the full initialization of L trees, but you need to show it here itself. Then we'll have to call a recursive function, because whenever we generate a tree, or even you must have used the same concept while generating a linked list. We use the same concept that for generating the nodes of nodes, we use recursive functions. Similarly, I'm using recursive function over here also, calling the same function again. Now you need to add an external condition for n is equals to 5. Whenever we will be having n is equals to 1, we need to return the list by adding only the one node into it. You need to return it as it is by only having one node in it, because it's quite obvious that for n is equals to 1 we will be just having a single node and we will be returning it as it is. We just don't need to do anything on it. No operation required for n is equals to 1. Now it's quite simple that we have taken a new list and we have just put into it a single node and we have returned it into the same function. Now we will be generating the right subtree of it. So for generating the right subtree, why did I take this 3? As I already told you, we'll be either taking or the odd number. So after 1, the only possibility for odd number will be 3. That's why when I told you that we need to use this condition, I told you in the previous minutes that we need to use this condition. We need to understand that why am I using it. This will give me only the odd numbers. Because you can say, it's quite obvious. Let me explain you the funda behind this, that why am I saying that this will give me the odd number. Because assuming I am very much confident about that I will be the odd number only. I am only considering 1, 3 and 5. That means only the odd number in this case. Now, this thing is also obvious, and n is also obvious that it is also going to be only the odd number. And here 1 is the also odd number. So, if I'll be writing this n minus I plus 1, this is the similar form of it. I'm just explaining you why have I written n minus I plus 1. Now this I plus 1 is which type of number? This is also odd, this is also odd. This is a even type of number. Okay. Now n minus even number. This n is an odd number and even number is an even number, of course. Then when we are always subtracting odd number and the even number, that means we are subtracting even number from the odd number, this will always be giving me an odd number only and only. So this was the funda which I was saying that why we'll be using this condition. Just no need to cram it. Try to understand each and every step. Each and every step has a logic. So where we were over this condition that yes, we need to generate a right subtree. So for right subtree, we have passed 3 here because n minus I minus 1 was the condition we need to use for generating the right subtree. And here is 5. 5 minus I here is 1 and 1. This will result me to 3. Then we are getting again a new list of tree node type data structure. Then we will be traversing the loop again where I is 1 and this whole processing will be done again. You can see we'll be generating its left subtree again where we'll be having only one node. Then we are generating its right tree again. Similarly, we are having only the one node. This will wholly result in generating a node similar to this kind. And let me explain you how is this node generated. Whenever you are supposed to generate a node, you need to pass this condition, not condition, but this statement. Now what is this? Let me explain you. So as you must be knowing that for that whenever we are building a tree or a linked list, we always create a specific class for it or a struct type data structure we use. Let me explain you through the Leetcode what I am trying to say. You can see that for this tree node, we have already been given a definition that for struct tree node, we are having a value type data type, we are having a left pointer, we are having a right pointer, and why we are being given this, because we have to generate a binary tree, full binary tree. So we have been given these conditions. So we have to pass this new tree node statement because we'll have to generate a new node. For generating a new node, we'll have to pass the value of the node. As in the question we have been asked to put the value as 0, so we'll be passing 0. Then we have been asked to pass the left node and the right node for generating the tree. So this we'll have to write this statement over here that list, because list is a vector type, we'll be using pushback list.pushback new tree node and this whole statement over here. Then you can see we'll be able to get this whole tree with n is equals to 3, and later on we'll just have to return it to our function where we have called it for generating the right subtree. You can see over here. here. So now we have left subtree, we have right subtree, we just need to club it up. You can see for generating the whole node. We are doing the same thing again which we have done over here where we got the left like the right subtree with 3 node. Now we'll be getting the whole tree with n is equals to 5 with one possibility. Similarly, we'll be getting the similar kind of tree when like this was the case when I was 1, like for the first iteration. This was a dry run which I just explained you. Now for I is equals to for the next case we'll be having the I is equals to 3 because we have incremented it with 2. You can see, as I already told you, we just need to take only where the code is, yeah, it's here. As I told you, we'll be incremented it by 2, so I'll be 3 now. Now when you will be solving it with the same dry run as I did now, you will be getting the left subtree here as nodes having 3. Then you will be getting this subtree, not subtree but left subtree, then right subtree with node 1, and then you will be getting a tree as this. This kind of tree will be generated where we are having 3 nodes in the left subtree, and in this case we are having the 3 nodes in the right subtree. So you can see all the possibilities we have got here. So this was the whole illustration. Now let's try to understand what will be the time complexity of this approach which I have explained you now. Till now I haven't discussed over that whether I have used DP or not, because this lecture, this whole series is all about DP, but I haven't even talked about the DP concept here. The above concept was only based on recursive approach or the basic approach. It was a recursive approach. So I can easily say we are talking about the full binary search tree, and the time complexity of full binary, not search, it's full binary tree, I would say. Yeah, it's full binary tree. So the time complexity of full binary tree is always 2 to the power h minus 1. Alright. But here we have already left the even number of nodes. So we'll be saying that we have the possibility for 2 to the power n by 2 only. So the time complexity in this case is 2 to the power n by 2. And the space complexity will be similar to it, 2 to the power n by 2 itself only. Now we can also optimize the above approach using the DP concepts. We can use, okay, let me explain you how we can use the DP concepts. For DP, we just need to remember 2 things. That the solution we are trying to find has the recursiveness, and the second thing is overlapping subproblems. So we need to understand, we can see from here that we are having so many overlapping subproblems. You can see I have calculated the value for n is equals to 1. Here also I have calculated the same value. So I am calculating the same value for the same number of nodes again and again, which is again a overlapping subproblem. So for avoiding this, we can use a memoization technique. What we can do is we can take we can use a map here, and we can use an unordered map. Yeah, let me write it properly. We can use an unordered map where key will be the nth node about whom we are talking, and the value will be all the possibility of it. The node type. What we can do is we can already check if we already have stored the value for n is equals to 1, we already have stored the solution for it, then we can retrieve it from the map. Alright, so there are basically two types of approach we can use in DP. We can either use the memoization technique, we can use here unordered map which I have discussed now, or we can use a bottom up approach. Now, as I already told you about the memoization technique, let's have another approach with us, which is bottom up approach. Let me take you to the Leetcode here. I have solved this question by bottom up approach. You can see we are checking this condition that whether it is odd or even. Whole code and the whole concept will be remaining the same. We are just going to have this iteratively. In all the previous approaches, we have used a recursive approach, but here we are using, I'm talking about the iterative approach. I'm using the vector of vectors. Why did I use a vector of vectors? Because for each node, I'm storing all the possibilities of that respective node, all the possibilities of full binary trees for that respective node I'm storing. So I'm using this vector of vector. Then for n is equals to 1, we can manually push this node because we all know for n is equals to 1, we'll be having just one node with value 0. Now, so I'm starting it from 3 because I know that we don't need to take 2 because we already know we'll be considering only the odd nodes. So we have taken it from 3. Why? As I've already told you the reason for plus, why did I increment it by 2? Because again we are going to only access the odd nodes. Then for I, we'll be taking 1 from count minus 1. Then again here I plus 2 equals to 2. The same condition as it is the similar as I have talked about this I and n minus I and n minus I minus 1. So these two counters we'll be maintaining over here for I loop and for the j loop. You can see count minus 1 minus I. And then in this for loop we'll be generating the node and then we'll be pushing the whole tree for that corresponding nth node, you can see. So again, iterative approach is easy, but you should always start the solution from the recursive approach for the dynamic programming questions. So, and one thing you just need to remember, all the approaches have the similar kind of complexities. You can see in the editorial also, here we are having the availability of editorial. You can easily read this and you will be having a detailed explanation of this. It's very easy and it's very intuitive too. You must read the solution. Alright, so thank you and everyone and thanks for watching my video.